Good morning. The topic today we are going to discuss is SIC assembler. So first, before going to the topic, the prerequisites are the student should know what is an assembler, functions of an assembler. So first, what is an assembler? Assembler converts your assembly level language into a machine level language. That means an assembly level language will be in the form of a high level language which is understandable by human, and machine level language will be in the form of zeros and ones which is understandable by the computer. So function of an assembler is it will convert your high level language into machine level language. So for today we are going to see an SIC assembler. So in SIC assembler it will convert an SIC program, that is an SIC assembler program, into a machine level language. So for this we will see a program today, and that program will be converted into an machine level language. So what are the steps involved here? So the first step is, first we have to take the program. The second step is assign address to all the instructions. And the third step is generate object code generation. So for object code generation, you need the address as well as you need the value of opcodes. Fourth step is writing the object program. So object program is nothing but the program that can be understood by the computer, that is the machine level program. You have a program that is an assembler program. The assembler program, first step is assigning an address, second step is object code generation where you need the address and value of opcode, and the fourth step will be object code creation. So object program creation, for object program creation you will be having three types of records, that is text record, header record, and end record. So we will see the format of each of these things. So before going into this, we should know what are the addressing modes supported by SIC. So in the first video lecture we might have learned that. So first there are two addressing modes. First one is direct addressing mode, and second one is indexed addressing mode. So you have a single format. The format is opcode and X and address. So it is 15 bits, it is 1 bit and 8 bits. So totally all instructions supported, SIC supports instructions of 24 bits. So all instructions are 3-byte instructions. Since 1 byte is equal to 8 bits, all the instructions will be 24 bits. So instructions, there can be two addressing modes. One is direct addressing mode and next one is indexed addressing mode. Direct index addressing mode can be understood by a simple technique, that is if you have X as a part of your instruction, then it is index addressing mode. For example, we will have an instruction like stch buffer comma X. That means X is a part of instruction. So this type of instruction actually is index addressing mode. Another instruction stl retadr. In this instruction you don't have X as a part of your instruction. Here you have this is label field and this is opcode field. You have an opcode and a label, and this is direct addressing. So two types of addressing mode, index addressing mode as well as direct addressing mode. Index addressing mode is represented by the value of X, and direct addressing mode there will be no X. So we'll see the program first. Consider you have a program like this. This is your program. We will see it step by step. So first you have a program. The first line specifies copy start 1000. So before going to the program, we should see there are some assembler directives. Apart from instructions, there are assembler directives, that is SIC assembler directives. So the assembler directives are start, end, byte, reserve byte, word, and reserve word. So already we have learned about this byte, reserve byte, word, and reserve word, but start is new. Start means it specifies the beginning of a program. So this will not perform any operation, just it will specify the beginning of the program. End specifies the end of the program. Also, to the end, optionally you can have the first executable statement. So with end, if you have any word there, that word specifies the starting of the program. Start specifies the beginning of the program. Near the start, you can have the name of the program. For example, the example we are going to see will be like this: copy start 1000. That means start specifies the start of the program, copy specifies the name of the program, and 1000 specifies the starting address of the program. And I have already said end. End specifies the end of the program, and if it is end first means end, and first is the first executable statement. So next, byte, you know already byte, it will reserve 1 byte and it will store something. Reserve byte will reserve 1 byte, but you can store some whatever comes in the program. And word specifies 3 consecutive bytes from a word, and reserve word specifies you are reserving 3 bytes for later use. So these are the assembler directives, and each assembler directives will have its own function. Start specifies start, end specifies end, byte will reserve a byte, byte will reserve a memory location, a single byte, and you can store something into that. Reserve byte will reserve 1 byte, and only during the runtime we know what will be the content. And word will reserve 3 bytes, and reserve will also reserve 3 bytes. The difference is word will have content and word will not have content. It will be known only during the execution of the program. So we'll start the program. So here we have the first line, copy start 1000. That means start is the name of the start is the starting of the program, and copy specifies the name of the program, and the starting address is 1000. And we'll search for end. End is at the end, and it specifies first. That means first is the first executable statement. So this is the first executable statement. So in this program, this copy program has, the work of the copy program is from the input machine, that is F1, it will copy some content, and that content will be kept in a buffer, and later the content from buffer will be transferred to an output device called as 05. This is the work of the program. That is, you are going to copy some content from a machine called as F1, and you are going to store into another device. That machine, name of that machine is 05. So here what happens is, in SIC, for an input and output operation, first you have to test the device. If the device is free, you can go for reading the data. So first we will test the device F1. If it is free, we will read the data, and after reading the data will be transferred to buffer. From the buffer, before writing into 05 machine, first you have to again test the device, test 05. If the device is free, you can go for transferring the data. Otherwise, we cannot transfer the data. Otherwise, you have to wait. So for reading, you have a function called as read record from F1, and for writing you have a function called as write record from machine 05. That we will see. So we will see the program. This specifies the program, and this is the address. How does I'll tell you how does the assembler assign address to the program. Now the program is written by the programmer. Now it is the work of an system software. Our system software is assembler. So the assembler have to assign address first. So the first step is assigning address. We'll see how this assigning address takes place. So as we know, the first step is copy start 1000. Copy start 1000. This specifies the start of the program, and copy is the name of the program. So 1000 is the memory location. So from end we understood that first is the first executable statement first, and I am assigning 1000 here because the program should start from 1000. So I have assigned 1000. Then already I have said all the instructions are 24 bits. That means all instructions are 3 bytes. So first instruction, for example, the instruction is STL RETA DR. So here STL is nothing but your opcode, and this is your label or a memory, we can say. So STL RETA DR, once again I will write. So STL RETA DR is your instruction, and this instruction will occupy 3 bytes or 24 bits. So STL starts from the address 1000, so it has to occupy 3 bytes. 1000 it will occupy, 1001 will be occupied, and 1002 will be occupied. All these 3 memory locations will be occupied by STL. So the next instruction, C loop J sub RD REC. Next instruction is J sub RD REC. So what is J sub RD REC? This is another instruction. These instructions should also occupy 3 bytes. So first instruction has occupied till 1002. So the next instruction must occupy from 1003. It occupies from 1003. So this instruction will run in 1003, 1004 and 1005. So the next instruction must come from 1006. You can see here 1006, that is LDA length. Then now you can have STL RETA. There is an instruction. What is this first? First specify the first executable statement, and C loop, this is the name of the loop. So this is the instruction, this is just the name of the loop, LDA length. So it comes from 1006. Then one more thing, all these addresses are in hexadecimal format. So from 1000 we will start like this: 1000, 1001, 1002, 3, 4, 5, 6, 7, 8, 9. After that it will be 0A, B, C, D, E, F. Then after that the next step will start 10, 10, 1011, 1012, 1013, 1014. It will come up to 1019, then 101A up to 101F. So after that it will be 1020, 1021. It will go up to 1029, then 102A. It will move up to 102F. The next step will be 1030, 1031, 1039, 103A up to 103F. Next can be 1040 up to 1049, then 1014A up to 1049, 104F. This is how in a hexadecimal format works. This is how hexadecimal format works, and we'll see the next instruction. We have come up to 1006. This LDA will occupy 1006 to 6, 7 and 8. So definitely the next instruction, that is compare, will start from 1009. So this instruction will occupy 9. So after 9 it will be 100A. So what is 9A B? So next instruction will start from 100C, then 1CDE, 100F. Similarly, all instructions will specify all instructions with the help of, that is adding 3 bytes to each instruction. So all instructions come in this format, that is, you'll use hexadecimal format, and when you are adding 33 bytes, it will be added. And when you finally reach here, then instruction is in 1039, and the instruction here is buffer RE reserve byte 4096. Buffer reserve byte 4096. So if I have reserved byte 1 means I will suppose this instruction is like this: buffer reserve byte 1. That means I have reserved 1 byte. So here we have reserved 4096. So 4096 is in hexadecimal format. So I have to convert this into decimal format. So for that I will do like this. It is divided by 16. I will get 2, 5, 6. You will get 0. Then 16. 16 into 16 is again 256. Again I will divide by 16. 1, 16. So this is 1000. So instead of 4096, I will reserve 1000 bytes. That is buffer. Actually, this looks like this: buffer reserve byte 1000. So I have reserved 1000 memory spaces. 0 to 999 memory locations will be reserved for this buffer name. So now when you see this instruction, so this instruction will start from 1039. So it is buffer reserved by 1000. You have reserved 1000 memory spaces. So the next memory should be 2039. So only at this position we will add 1000 because here we have reserved 1000 memory locations here. So you can see the next instruction 2039, 39. Then after 9 it will be A, 3A, 3B. So the next instruction will be 3C. Similarly, all instructions will be assigned locations here. So we might have understood how does a memory is assigned. Memory is assigned by means of adding 3 bytes whenever an instruction is encountered. Suppose if an instruction starts at 2072, that instruction will complete at 2073 and 74. So the next instruction will start at 2075. This is how an instruction is assigned an address. Address assigned takes place. Similarly, we'll have one after assigning address, the next step is generating object code. So for object code, first you need the value for mnemonic operation code. So for example, you might have seen an instruction like this: STL RETADR. So RETADR is nothing but a label, and STL is something which is done by the assembler. Here, what happens is, for each instruction code, this is an instruction code, the assembler has given some values. So while they are designing assembler, there will be a table for that STL. They will give some values like 14. Suppose if you have the value called LDA, that will be given as 00. We will see that. Consider the program. See here I have the mnemonics, and for each mnemonic this value is given. This value is assigned by assembler. These values are not given by, these values are not specified by the programmer. These are values already given by the assembler. So while designing an assembler, internally these values were written. Now we are going to generate object code. This is the work we are going to do. So for giving the object code, first what you have to do is you have to look at the instruction. For example, first instruction is STL RETADR. So STL, what is the value of STL? We have to find out. STL value is 14. So I'll do it here. STL RETADR. So what is the value of STL? STL is 14. And RETADR. RETADR can be defined inside the program. So we'll search for it. RETADR is here in this program, and it is given as 1033. So STL is given as 141033. I will see another one instruction, JC loop. Consider this instruction, JC loop. I'll tell you how does this work. Consider an instruction, JC loop. So J is a opcode, C loop is a label. So we can search in this mnemonic value. J is 3C and C loop can be defined somewhere inside the program. You can see where is C loop. We will find out. C loop is defined in the program before to this. So the value of C loop is 1003. So 1003. So JC loop is interpreted as 3C1003. You can see here JC loop 3C1003. Similarly, we will do another one instruction, J sub write record. So J sub write record. J sub write record. So what is J sub? J sub value is 48. So I'll write as 48 write record. So you can find write record here 2061. 2061. So this is your answer, 482061. 482061. This is how you will generate a value. This is about instructions. Then suppose if you go for this word, so what does this word will do is, it will just write the value, that is word is 3 bytes. If it is 3, it is written as 00003, that is it is represented in 6 bits. So first 2 bits will be 0, next byte is 0, another byte is 3. So if I am representing 0 word 0, all values will be 0. Then for reserve word, we don't know the value, so it is kept as blank. Reserve word is also again kept blank. Reserve byte is again kept blank. So if you see this byte, you can see here. So input byte F1, that means F1 value will be stored, directly stored. We will see another one instruction, that is STCH buffer comma X. You can see here STCH buffer comma X. See, what is buffer comma X? Since X is a part of instruction, this X is nothing but index addressing. So if it is an index addressing mode, we cannot find the values directly like that. What you have to do is, you have to draw the instruction format. The instruction format is opcode, then X, then buffer, that is address. So you can see here opcode value of STCH is 54. So I'll write 54. It should be represented in 8 bits. I'll represent that. Then since X, if it is index addressing mode, X is 1. If it is not index addressing mode, X will be 0. So buffer. So we have to find the address of buffer. Address of buffer is 1039. I'll write here 1039. Now this address should be represented in 15 bits. This is 1 bit and this is 8 bit. So we'll do like this. I'll write here 54 in 8 bits. 5 will be represented in 8421 method. 5, 4 plus 1, 5. So 0101. 0101, and 4 will be represented in 8421 method. 0100. 0100. This is 5 and this is 4. Then X is 1 and 1039. So first we will represent the last bit. 9 is represented in 8421 method. 1001. 1001. 3 will be represented as 8421 method. 0001. 0001. And 0 will represent as 000. And now we can we have to make a small adjustment, that is it should be represented in 15 bits. So I have represented 3 4 4 4. I have already used 12 bits, so the 1 should be represented 3 bits, that is 4 to 1. So it will be 001. 001. Now I'll combine this. 5 is there, 4 bits, this is 4 bits 4, and these two will be combined. 1001, that means 8421. 8 plus 1, 9, and this is 0, this is 3, 9. So the value of stch buffer comma x will be 549039. Here it is represented as 549039. This is how I will generate all the object codes. Here in this program you will have two index addressing and all the others are direct addressing modes. So from this object code, next we have completed the object code creation. First what we did is we have assigned address. From assigning address we have gone to create object code. The next step is writing the object program. For object program there are three steps. So first, an object program will contain three records: header record, text record and end record. These are the formats of header record. So header record contains four things. The first one should be H, and second one should be the program name, that is program name is 227. That means you have 6 spaces to write a program name, and the starting address of the program, it should be written in hexadecimal, and length of the object program in bytes should also be written in hexadecimal. Then text record, the first letter should be, it should be your T, and second column it should contain starting address of this text record, and the third one should be length of the object code in bytes, and the last one is object code represent. See, here we have 10 to 16, that means you have 60 spaces. If it is 11 to 69, you can easily say that you have 59 spaces. Since we are starting from 10, I will add one more thing, that is 60 spaces. Then end record, it will have E as well as the address of the first executable statement. So we will write the text record now, that is we will write the object program by seeing the object code. So we will write the object program. The first record should be header record. So first column it should have H, second column 2 to 7, so we will have 6 spaces. Second space should contain the name of the program. Name of the program is copy, so I will write COPY, copy, so it occupies 4 spaces. So 2 spaces will be left free. The next, starting address of the program. Starting address of the program is 1000. So here it can have from column 8 to 13, so 8, 9, 10, 11, 12, 13, 6 places. So the first 2 places are 0, second spaces will be 1000. So starting address is 1000. The next, length of the program. See, length of the program can be calculated like this. The length of the program is last address minus starting address plus 1, because we start our program from 0th location. So the last program, the last instruction has occupied till 2079. So last one 2079 minus 1000 plus 1. So 1079 plus 1. So it will be 1078. 9 plus 1. This is hexadecimal. The next number should be 1078. So 001078. This is your header record. So hope you might have understood what is header record. So it should contain H. Then it should contain the name of the program, which is copy. Then I have written the starting address of the program, which is 1000. Since it is 6 memory spaces, I have written 1000, and before 1000 I have added 2 spaces. Then last one is that is the length of the program, 14, 15, 16, 17, 18, 19. So again I have 6 memory spaces, but my program length is only 1007A. I have added 2 spaces here. This is how you write the header record. Next, we will write a text record. See, text record, first one it is T, second one is starting address of the object code in this text record. See, the most important thing you should understand here is we have to represent object codes. So you have 60 spaces. Each object code is of 6 in length. That is, each object code size is 6. So if you want to add 60, then 6 into 10 you will surely contain 60. So I can add in the first text record, I can add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So till 00102D, all these object codes can be added. So all these object code can be added. So we'll come to the second and third part later. Before that, I'll write one by one. I can write here 141033, 6 spaces are over. Next 482039, 482039, 12, 001036. The next 281030, and later 301015. Similarly, I'll write till 00102D. Now you can see the previous thing, you have to find the starting address of the object code of this text record. So the first text record's starting address, that is 1000. I'll again represent it 001000. Next, the next is length of the object code of this record. So only 2 spaces I have to represent. What is the length of the object code? See, length of the object code you can represent it as we have started from 141033 and we have stopped at 00102D. See, so the instruction is LDA3. You have to come here. This instruction starts at 101B. So the instruction, this LDA3 will occupy 101B, 101C and 101D. So it will come till 101D. I have to find the length of this object code. So already we have seen how to find the length of the program. Here similarly we'll have, it starts from 1000, it ends at 101D. So we'll have 1D will be the answer. Since it starts from 0, I have to add one more thing. So the length will be 1E. So only 2 bytes I will represent. So T is text record, then it comes from the length of the starting address of this text record, that is first text record starts at 001,000. Then I'll write all the 10 text record because it gives you 60 spaces. Then the length will be calculated by finding the last text record where it ends and subtracting it from the starting, adding 1, you will get 1E. So if I have to write the next text record, you can see here, it should start from 0, the next one, 0C1036. So text record, next text record. So the starting address will be 101E, 00101E. Then we will find the length at the end. See, you can see here 1, 2, 3, 4, 5, 6, 7. So you cannot go here because you have reserved 1000 spaces. So I'll stop it at here. So you can write like this: 0C 101 0C 1036 will go till 00000. Now what is the starting address? See here, it is 1030. So that word will occupy 1031 and 1032. So you have to subtract 1032 minus the starting address of this one is 101E. 101E. So for subtracting 1032 and 101E, it will be done like this, that is 2. And since it is hexadecimal, the carry will be 16 plus 2, 18. 18 minus E. So E is, A is 10. So B will be 11. C will be 12. D will be 13. And E will be 14. So 16 plus 2 is 18. So 18 minus 14, this is 4, 1, 4. So already I have said, since it starts from that position, you have to add 1. So the answer will be 1, 5. So second text record will be 1, 5. So similarly, you have to write other text records, and we will see how is end record written. So the format of end record is E and address of the first executable statement. So E is E, then first executable statement address is, so first, so it is 1000. So it should be represented in 2 bits, 16 4 bits, so 00,000. This is how we will write an object program. So see, object program will contain header record, text record, The text record can be, you will have only one header record, you can have more than one text record, and you will have an end record. So here, what we have discussed today is we have seen a program. The program was converted into object code, and object code, by using object code, we have written object program. So this is a two-step process. The program, it was an assembler program. Using the assembler program, you have seen the object codes. That is for generating object codes, we have taken the address, and also we have used the mnemonic values to find the object code. From object, after converting all the instructions into object code, we have written the object program. So in this video lecture, we have seen what is an assembler, how does an assembler works. Here we have taken a program. For the instructions of that program were for each instruction we have assigned address, and after assigning address, what we have done is we have created the object codes. Object codes are created by using the assigned value, as well as we have used the mnemonic values, which is already written by the assembler. From the object code, we have generated the object program. For generating object program, we have three types of record. First one is header record, second one is text record, third one is end record. Now a program which was in high level language, which is an assembler, is converted into a machine level language which should be understandable by the computer alone. When you see this object program, which cannot be understood by the humans, but it will be understood by the computer. So in this class, we have discussed about the conversion of a program into a machine understandable from. Hope you understood the lecture. Thank you.